I'm going to generate a lot of random numbers with Excel to show you the expected distributions of sample statistics. You can find this worksheet in the Excel Companion's Probability Distributions Workbook, which you can download for free from the Excel Companion's website. This is a good video to watch as you're studying the foundations of inferential statistics. Some of the essential concepts of inferential statistics can seem abstract and dry, but you can actually see the concepts in action by simulating a data generating process. It can help you see the concepts and understand them better. The examples I show in this video are similar to an old school class exercise where everybody flips 40 or 50 coins 40 or 50 times, calls out how many times they got heads, and the professor plots the class-wide results on the board to show the class the distribution of the number of heads. My Gumballs example in this video is a lot like that. When you watch these two examples, I hope you see that the statistics we obtain from random samples can fall into a specific pattern. That's what the central limit theorem tells us, and we can see it happen. There's a special kind of order to the randomness of random samples. In these examples, I'll generate a lot of random numbers, but I want you to look at the pattern that emerges in the distributions of sample statistics.
This is the estimating proportion of red gumballs example. We're told that a giant gumball machine contains 0.60 red gumballs. That means 60% of the gumballs in the giant gumball machine are red colored. And it asks, how accurately could you estimate the proportion of red gumballs in the machine using samples of 40 gumballs? Now we know that it actually contains 0.60 red gumballs, but we're going to do a simulation of drawing samples of 40 gumballs to figure out how accurate samples of 40 gumballs would be, how close to the actual parameter of 0.60 we'll get with these 40 gumball samples. We can do this with the probability distributions workbook. I'm going to go to the population proportion example page. Now you can fill in for reference the population parameter and the sample n and some details about the extent of the simulation we'll do. So the proportion, we'll enter 0.60, and the sample size is 40 gumballs. And on the worksheet, there's a bunch of zeros. I just started with the all zeros worksheet. We're going to fill this in now with some data simulation. So to actually simulate the draws of 40 gumballs each, I'm going to use the data analysis tool pack, random number generator, the terminology or the dialogue's maybe a bit tricky. The number of variables, or how many simulations we'll do. And to illustrate this, we'll do 100 simulations. So we'll be drawing 40 gumballs 100 times. And the number of random numbers is the size of the sample. So in this case, it's 40. We're using a binomial distribution, our distribution that's like flipping a coin, except the coin here is not 50-50, it's 0.60, because 0.60 of the gumballs are red. And number of trials is still 1. That means each sample is one. Each of the 40 samples consists of one gumball. I'll use this random C 1 2 3 4 5 so you can replicate it. The output range looks in the right spot. I want to do the top left corner of our area and click OK. Do overwrite data. You OK? I'm going to pause the recording for a moment. Okay, now Excel has done its thing with the random number generator and outputted ones and zeros down the column. So you can see on sample number 1 here in the G column, we've got 40 random numbers, ones and zeros, and the estimate is telling us that this first sample got the number right, just right. 0.6 of the gumballs, the ones indicate red gumballs. In this sample, 0.6 are red, but in the second sample, you can see that it has overestimated the number of red gumballs. In that second sample, it would have estimated 0.625, so a little bit over. Then you can kind of work your way down. We'll have actually 100 of these in the simulation for how well we have estimated the correct proportion of red gumballs. Gets it right sometimes, but then a little high, a little low. Come over here to the analysis section. I want to zoom in a little for you. We get a better idea of how accurately 40 gumball samples have estimated the true proportion. The lowest we got was 0.40, which is quite a bit lower than 0.6, and the highest we got was 0.75, which is quite a bit over quite a bit of overestimation. The standard deviation of estimates, also called the standard error of the estimate, is 0.075. Now, what does that mean? That means that on average, our estimate was 0.075 away from the true value. So the standard amount of error we had because of random sampling and using small samples, and of 40 is a fairly small sample, is 0.075. So on average, we missed the true value by about 7.5%. Now we're going to examine some interval level data with the sampling distribution of a mean using this mean class test score example. It reads, researchers administer standardized tests in 50 student college classes. Researchers know the mean test score in the student population is 100 with a standard deviation of 10. How close to 100 will the mean class test scores be? So you've got samples of 50 students and want to know, when we sample 50 students, how close will the class averages be to the known population mean of 100. I'm going to simulate this with the population mean example, and I've cleared out the data on the worksheet so I can start from scratch. What I'm going to do is use Excel's random number generator to fill in these columns of 50 test scores each, and I'm going to do that 100 times to simulate drawing 100 classes of 50 students each and examining their test scores. So to fill in generate the random numbers for the raw data, I will use Excel's data analysis tool pack with the random number generator, and looks like that's for us. So we're going to, the number of variables to generate is 100 for 100 samples, 100 classrooms. The number of random numbers is 50, the number of test scores in each group. To simulate this, we will use a normal distribution with mean 100 and the standard deviation. So the test scores are drawn from a normal distribution with mean 100 and a standard deviation of 10. I'll use this random seed 1, 2, 3, 4, 5 so you can replicate this with your own version of Excel. And for the output range, I'll use the upper left corner of the area I want the random numbers inserted. So I'm going to click OK to generate these random numbers. I paused the video while Excel was calculating the random numbers. It took about a minute, but you can see now on the sheet that for each column I have 50 random numbers, and I'll scroll over to the left so you can see that it's filled this in, 100 classes, 50 students each of these simulated test scores. Let's zoom in a little bit to see what the sheet is telling us. You can look at the samples are numbered, and for each sample it gives us the estimated, it calculates the mean test score to estimate the mean on the test, and tells you how much the estimate in the classroom deviates from the known population mean. So in this first class, the estimate of the mean was 101.3 from those 50 students, and that's 1.3 above the population mean. In the second classroom, very close, 99.9, just under the actual mean of 100. And you can see a variety of scores, and they're going to deviate randomly because we are drawing a random sample. But the question is, these values, given the underlying distribution of test scores and the number of students we're sampling, how accurate will these estimates be? How close will they be to 100? The analysis section over here gives us some ideas. The mean of the estimates, the mean of 100 means is very close to 100, 99.98. The minimum estimate of all the classroom samples is 95.49, and the maximum estimate is 103.90, about 5 points too low, about 4 points too high. Now here's an interesting part, the standard deviation of the estimates. It says that on average, our estimates deviate from the true value by 1.48 points. And the standard deviation of the error is the same value, 1.48. I'm going to look at the histogram here of the estimates. A little hard to see, so I'm going to pull this out for a minute. And this is a plot of a histogram of the estimates. So you can see the highest bar here is the interval that contains 99.9 to 100. So all the ones close to 100. And then roughly symmetrically tails off from the interval that contains 100 to either side. So most of the estimates are close to 100, and then they tail off as you get lower and tail off as you get higher. The histogram of the errors is going to look the same pattern, but the number's a little different because this is going to scale to 0. An estimate of 100 has 0 error, so that would be the biggest bin here. And then it's saying, you know, that on the upper end, some estimates are about up to 4 points higher, and on the lower end, about 5 points lower. Here's something to look at while we're examining these scores. The minimum value, maximum value, and the variable standard deviation. Now, what this is telling us is in all of the test scores, 50 students times 100 classes, the lowest observed value was 66.23, and the highest observed test score was 140.09. And you can compare that to the lowest mean and the lowest and the highest mean, and you can see that the individual test scores vary a lot more than the mean test scores do, which makes sense. And also look here, the variable standard deviation. So in all the variable standard deviation means in all these groups, on average, the test scores of students varied 10.02, which is approximately the value of the population standard deviation. And you can see another example here where the test scores at the individual student level vary a lot more than they do at the classroom level. The variation at the individual student level was 10.02 in the test scores, but the standard amount of deviation of the classroom level estimates, of those 100 classroom level estimates, was 1.48. So in this example, fairly accurate estimates of the population mean.